My name is Joydas Poirago. Currently, I am doing PhD in IIT Kanpur. From today onwards, we are going to learn quantum mechanics. As you all know, the logic of quantum mechanics is little bit absurd to us. Why it is absurd to us? Because our brain think in classical way. It doesn't think in quantum mechanical way. It is a good approach to learn quantum mechanics by think in quantum mechanical way. So for that, we are going to follow the approach of the book named Modern Quantum Mechanics by J.J. Sakurai. In this book, they started the quantum mechanics from a concept which has no classical analog, that is spin. We are also going to start quantum mechanics from the same concept, and after learn little bit of quantum mechanical concept, we are going to solve the problem from the same book. This book, Modern Quantum Mechanics by J.J. Sakurai. Spin was experimentally first observed in Stern-Gage experiment. What is the Stern-Gage experiment? A directed beam of Ag atom passes through the magnetic field, and after passing through the magnetic field, it hits a screen, and that screen measures the deviation of the Ag atom. Now, if the Ag atom deviate from the path in the presence of the magnetic field, that means Ag atoms have some magnetic momentum. From where this magnetic momentum comes? Ag atom has a single unpaired electron. If it possesses some spin angular momentum, that can give some magnetic momentum. That mu means magnetic momentum should proportional to the spin angular momentum is. Now if it has some magnetic momentum mu, then what amount of force that will act on Ag atom? That will be Fz equal to minus del z into mu dot b. Here B is in this direction, we assume that B in the z direction and mu is in the direction, the angle will be theta. Then it is mu cos theta into del z of Bz. Since the atoms in the oven are randomly oriented, there is no preferred direction for the orientation of mu. If the electrons are like classical spinning objects, we would expect all values of mu z between mu z means mu z equal to mu cos theta. If the electrons are classical spinning object, that means mu can take value from plus mu to minus mu. That means a continuous beam of Ag atom should hit the screen, and the screen will look like this. But what is observed, Ag atom experimentally split into two different beams. Rather than splitting into a single beam, they split into two separate beams. Now, this phenomena has no classical explanation. And this phenomena is actually called space quantization. This means only two possible values of mu z is allowed. One is mu z equal to plus mu and another is minus mu. That means spin only can take value either in up direction, that means in the direction of the magnetic field, or in the opposite direction of the magnetic field. No intermediate value of the spin is possible here, and that is because of quantum mechanics. There is no classical explanation for this phenomenon. Now we'll study the quantum mechanics and its representation in the vector space. So vector space and quantum mechanics. Vector space and quantum mechanics. Here the question is, how can we express the term mechanical concepts in vector space? First of all, we study the Kate space. As we have seen in the previous Stern-Gulch experiment, the electron has two states. One is the up state and down state. Each of these states can be represented in terms of Kate vector. Any of these two states can be represented in terms of Kate vector. This can be represented, the state of the electron can be represented by a state vector. Suppose if the state of the electron is represented by alpha. Now this is the symbol of a Kate vector. Now this Kate vector contain all the information about the state of the electron, and it contains everything that we are allowed to ask the state. And this state vector, two state vector, can be added to make a new state vector. It's like a vector addition. But here the meaning of this addition is that electron can be in a such state which is combination of two other states. This is the meanings of this here. Now if we want to know some property, some property of that electron, which is in state alpha, how will we know? How will we know the property? Now question is, how we know the property of the electron that is in state alpha. To know that, we have to operate the state with some observer. If we want to know the spin angular momentum of an upspin electron, we have to operate with the state with angular momentum operator that will give the angular momentum, and the state remains in the same state. So that's how we'll know the observable of the state. Here the angular momentum is an observable for an electron which is in upspin, which is in state upspin state. Now we can give an example how this is happen. Suppose that our angular momentum operator is 1 0 0 minus 1. This is our angular momentum operator. Our state is 1 0 and 0 1. So if we operate J, this is upspin state, this is downspin state. If we operate in the upspin state, that means it will give 1 into 1 0. That means here the observable is 1 corresponding to this operator J. Similarly, if we operate J in the downspin state, it will give minus 1 as observable, and it is remain in the same state. That is the concept of an observer. And here up state and the down state are called the eigengates of the corresponding operator J, and that value we get by operating with J plus h car by 2 by minus h car by 2. These are the called eigenvalues or the observable corresponding to the state plus up and minus up. Now in general, any state can be written in terms of eigenstate of an operator. If we represent any state in terms of eigenstate of any operator, we can easily measure an observable corresponding to the observer A, and here Ca is a complex number. There is another important concept, is called brush space. Brush space is the dual of the Kate space. Corresponding to each Kate space, there is an dual corresponding bra space. Dual corresponding of bra space. This is the gate. This is the bra. Now there is a postulate that if C is in any number, is in any general complex number, then this state vector C into alpha, its dual correspondence will be C star is the complex conjugate of the number C. Now we want to define a product rule between two vector in the vector space. This is actually called inner product. Inner product is similar to the vector three-dimensional vector product, that if there is a two vector r and p, that the vector product will be r p cos theta. Here this is the vector product in 3D space. In bracket space, the inner product is written in terms of alpha bra first, then get beta. This is the inner product between the state alpha and beta. The physical meaning of the inner product is what fraction of beta is represented by the state alpha, or vice versa. Means what fraction of state alpha is represented by the beta. There is some postulate corresponding to this inner product. The first postulate is alpha beta is equal to beta alpha star. Here the alpha beta, the inner product, is a generally complex number. And alpha beta equal to beta alpha star. Second postulate is inner product between two same k vector is always greater than equal to 0, and this is equal to 0 only for when alpha is a null gate. And if alpha beta equal to 0 when alpha not equal to beta, these two states are called mutually orthogonal state. If alpha is not the same as beta, then if alpha, the inner product between alpha and beta equal to 0, then these two states are called mutually orthogonal state. It means that the state beta, the no fraction of the state beta cannot be represented by the state alpha. There is another concept in this inner product, which is normalization. If alpha equal to 1, the state is called normalized state. If any state is not normalized, then we can also normalize the state by dividing by this normalizing factor. This is nothing but an inner product. Now we will study operator. What is operator in the state space? Operator change the state. To change the state, we have to operate on the state by some operator. Suppose there is a state alpha. If we operate with a operator x, this operator will change the state alpha to beta. If the state remains same, this, suppose that x alpha is some constant into same alpha, then this alpha is called the eigenkate of this operator x. If two operators operate on same state and give same state, suppose two operator y and alpha, y x and y operate on the same state and give back the same state, then we call x and operator y are equal. Now there are some other postulate related with the operator. First, that the addition of two operators are commutative. That means x plus y equal to y plus x. But the multiplication of the operator in general it is not commutative. This is a very important concept for quantum mechanics. And if gamma is x alpha, then the dual correspondence, that is gate corresponding to the bra corresponding to this gate, will be bra alpha into x dagger. This x dagger is called adjoint of the operator x. This is nothing but x dagger is the transpose of the complex conjugate of x. Now I am giving an example how we can calculate this. Suppose operator sigma is 0 I minus I 0. Now the complex conjugate of sigma will be 0 minus I plus I 0. The transpose its transpose will be 0 I minus I 0. This same as sigma. Now this is a special property here. We can show that why we can see that sigma transpose sigma dagger equal to sigma. If any operator holds this property, this operator is called Hermitian operator. And Hermitian operator plays an important role in quantum mechanics. There are other kinds of operator too, similar to the Hermitian operator. There are other kind of operator which plays important role in quantum mechanics. One of them is unitary operator. Unitary operator. That is, if some u dagger operator u dagger u equal to u dagger is identity operator. The identity operator means if it operate in any state alpha, suppose that I alpha, it will give back the same state. It will not change the state at all. It is called identity operator. If any operator u has this property that u dagger u equal to u dagger equal to u dagger u equal to u dagger equal to I, identity operator, then this operator is called unitary operator. This operator also plays very important crucial role in quantum mechanics. Now we'll see a little bit about the outer product and an example. Outer product is basically a operator, not a number. As we know that this inner product alpha beta is a number, generally a complex number. Similarly, the outer product between two state space is an operator. It is similar to the 3D vector space. Suppose the inner product is 1 0 and between 1 0 is a number. The number is 1, and the outer product is 1 0, the column vector into row vector 1 0, which is a 2 cross 2 matrix. This is the outer product, this is the inner product. This is the inner product, this is the outer product. Another example of the outer product is the projection operator. The outer product between two same state vector. What it does? It project any other state vector into state alpha. That means if we operate this projection in some vector beta, we'll get that this represent the what fraction of alpha, what fraction of beta is represented by alpha. That is the projection of beta on the state vector alpha, and this operator is the projection. The what fraction of beta is in direction of alpha. It is similar as if there is two vector A and B, what fraction of B is in the direction of A, that is A dot B. That is that fraction of B is in direction A. The similar thing is represented by the inner product, and this is called the projection operator.